rush of new breaker technology is greater and faster than it's ever been. Here and now, more is being learned and more is being done in the science and engineering of electrical distribution and control than has been accomplished in all the years that this technology has existed. That accomplishment is every day's work for this group of talented, enthusiastic Cutler-Hammer people. They are good. They're the best in the business. And so are their products. The new Cutler-Hammer, the source for the world's most advanced and rapidly advancing circuit breakers. Inside this space, these layered steps of steel, Cutler-Hammer scientists and engineers perform one of the spectacular everyday feats of modern technology. They teach electric arcs to pirouette and dance. No small task, because an electric arc is man-made lightning. Dangerous unless you know what you're doing. Inside this space, the arc chamber of a circuit breaker, the task of making electricity safe, making it serve, has been one of the energizing arts of this century. Both science and engineering have worked hard at it, with good reason. A circuit breaker can be used over and over again, and even more important, it can be part of today's computerized electrical distribution systems. It can communicate and respond. The intelligent circuit breaker. It's a breakthrough in system design. Science and engineering are doing more today to advance the capabilities of circuit breakers at a faster pace than ever before. A lot of what's being done, in fact, the cutting edge of most modern advances, comes from the scientists and engineers who work at this Cutler-Hammer Technical Center. Here, the art and science that is basic to Cutler-Hammer's family of Westinghouse circuit breakers moves farther forward every day. At the center of this center is that dancing arc and some astonishing physics, chemistry, and engineering.
The temperature of the electric arc exceeds 15,000 degrees Kelvin, and few materials can hold that temperature for more than milliseconds. To hold and control an arc, you must use every form of basic science and answer a lot of questions. What shape should such structures take? What materials should be used? What spacing? What size?
Basic questions. And the answers change with time and advanced technologies. But the tools are here now to answer those questions and 1,000 more. The tools and the talent. The most important of those tools is the computer. At this Cutler-Hammer Technical Center, the computers of all these scientists and engineers are networked together. All important information is universally accessible. That shared knowledge mirrors the sharing of technologies that makes this amazing place a critical mass of advanced thinking. The power of the computer system is impressive enough in itself. Today's computer modeling allows these scientists and engineers to know more than has ever been possible before. Magnetic fields, the interaction of vector forces as a mechanism trips, the stresses created by pressure and torque. And much more is being learned every day about the arc itself.
We use state-of-the-art diagnostic tools to study the arc interruption process, and the results are used in the design of next generation of circuit breakers.
In this technical center, arcs are studied in thin slices of time. The tests are performed in high-power laboratories. The results are sent by modem, and the learning process is painstaking. A millisecond may be studied for a month. It's a task that will never end because no two arcs are exactly alike. Arc physics forms the center of the work here, but the physics, engineering, and chemistry of the materials that form these electrical circuit protective devices are a discipline in their own right.
The materials we use to make a circuit breaker have to be strong and resilient because of the internal pressures that are generated when a circuit breaker interrupts a major fault current.
The pressure inside a breaker case under fault conditions may exceed 100 psi. What materials can hold such strain and still be affordable? The search for the next material or process goes on here, always seeking the slightly better result, never quite satisfied. The process is as important as the physics. The strength of a breaker depends heavily on the way its case is molded. There are secrets in the fast-moving art of the molding process, reasons why these breakers have the strength to tame a lightning bolt and then go back to work. Even that is just the beginning of the challenge, because those same materials have to do a job at a level of molecular physics.
The breaker's materials are one of the sources of ionized gas that are generated inside.
Under a fault current, molecules are torn from the internal surface of the breaker's materials and given an electrical charge, forming much of the plasma that conducts the arc. So the materials, which look like a simple box, are part of the physics of the interruption process itself. A box that must be designed to create a particular kind of gas that's different. And the interaction of technologies doesn't end there. On the other side, those same materials are part of the mechanical device, which has its own demands.
The breaker must close the contacts with enough force to reduce the electrical contact resistance, but must also withstand electromagnetic repulsion forces, which can be up to 10 times the rated current of the breaker.
Clamp tight when closed, fly apart fast when opened. A tall order. Then consider the contact mechanism itself, where physics and engineering again blend to provide an ingenious method. In the Series C breaker, the speed of the opening motion, with the contacts separating at an acceleration greater than a bullet being fired from a gun, acts with the electromagnetic field to create this long curving arc. The arc limits the fault current and provides the Series C's outstanding current limiting capability. A simple arc, but to make it, you must interweave in an instant the forces of acceleration and electromagnetism. Add to that chemistry and basic electrical theory, some science, some engineering. Arc interruption is a marvel in a millisecond. That same basic science of arc interruption is also applied to our vacuum interrupters, a product that is widely acknowledged as the world's best.
Our challenge in vacuum interrupter is to make the arc behave until it is natural for it to go out. To accomplish that, we use many different contact shapes: spiral, petals, cups, axial magnetic field type contacts, which seem to control the arc best.
The arc doesn't stay in one place, which is basically a cooling process, and therefore the arc does minimal damage to the contacts, very little effect at all. That's the secret of the long life and reliability of these vacuum interrupters. Needless to say, it's taken a tremendous amount of experimentation, years of it, to get where they are today, and they're getting better at vacuum technology every day. Vacuum interrupters are actually assembled under clean room conditions. The manufacturing technique is a major part of the product superiority. Modern circuit breaker design, no small challenge. Physics, chemistry, the power of computer analysis, all the science and engineering of the modern circuit breaker. The advances being made here at this Cutler-Hammer Technical Center help make possible the reliable, productive electrical systems that energize progress in the modern world. And even that is just half the story. I want to show you this quiet corner of the Technical Center. Here, the evolution of circuit protection becomes downright revolutionary. This is the home of the Sure chip, a microprocessor, the computer inside more and more of these circuit breakers. It's a custom chip that combines the precise measurement capabilities of analog circuitry, the computational power of a microprocessor, and the flexibility of modern high-speed digital communications. In a space smaller than a square inch, the Sure chip packs nearly 1,000,000 transistors. It's a reliable, compact chip solution for a wide range of end products. Sure chip includes 3 types of computer memory: ROM for program storage, RAM for temporary storage, and a non-volatile memory for permanent storage of calibration constants, trip causes, and more. It has both digital and analog circuitry, multi-channel digital to analog conversion, and thousands of electronic highway circuits that are separated by no more than a few microns.
The microprocessor is a willing worker that will do what you program it to do. A major part of the work of circuit protection and control at this technical center is dedicated to the creation of innovative software, new commands for the components, assemblies, and system of a new era.
The possibilities of what a microprocessor can do are as wide and far-reaching as the imaginations of these designers. Make your Sure chip think like a breaker, and you leap ahead in circuit protection. That was first accomplished here more than a decade ago when Digitrip technology was introduced. Today, Digitrip design allows a system engineer to program his protection curves in a computer and download them to our medium voltage breakers. The possibilities are many. Make the Sure chip think like a meter or a monitor, and it tells you what's happening on your electrical system. Cutler-Hammer does that with its line of IQ products. Program the Sure chip as an analyzer, and it will give you instantaneous information: volts, amps, phase angle, kilowatts, alarms, trending, and a lot more. It quickly can give you the information you need to take the right action. In Cutler-Hammer's family of Westinghouse products, this is the IQ Analyzer.
It all begins with a microprocessor. It uses milliwatts of electricity within a silicon chip to control megawatts of power within an electrical distribution system.
And these microchips can talk to one another and to central computers. The traditional electrical distribution system is humming with conversation these days. Using a simple wire like this, as many as 1,000 different devices can communicate, 50 different kinds as far as 1.5 miles away from a central computer. Data flows in, commands flow out. It's a whole new world in safety and systems management efficiency, and it's developing rapidly. Here, let me show you something. I think there must be a drawer like this in every electronics development center. This is where they toss last year's best ideas. And in this drawer, I found some interesting history. Here is the brains of a breaker of just 10 years ago. Few microprocessors, lots of circuitry. 5 years later, the microprocessors are doing much more of the work, and these brains are going into smaller breakers. A few years later, smaller still, and even smaller breakers are getting smart. Today, a single Sure chip does all the thinking, and Cutler-Hammer is putting brains into even its smallest molded case circuit breakers. It's just a drawer, an engineer's family album, but its contents show why the whole art of electrical system design has been revolutionized in the past few years, and also why the years just ahead are filled with promise. Milliwatts controlling megawatts. We're seeing the exciting beginnings of all that can be done, all that will be done. The power of the computer age, of our ability to digitize and analyze as never before, has opened a whole new era in the technology of circuit protection and control. And where these Cutler-Hammer scientists and engineers work, the pace of development is hot and fast. New designs take form first on the computer screen. The computer data can be transferred directly to laboratory workshops that use CAD/CAM programs linked directly to CNC machining centers. Prototypes can be produced in hours rather than days. Prototype manufacturing hurries the finished design to factory readiness, getting each new product to market quickly and